So hi everyone. This is week 3 of the combinatorics class. So today we learn about inclusion exclusion principle, surjective functions and derangements. And so the inclusion exclusion principle is a very general and very powerful concept. And so this is 8.1 up to 8.3 in the book. So let's start by considering a simple situation. So assume we have two sets. So this is a classical Venn diagram. So let's call it A1 and A2. And you want to count how many elements lie in the union of these two sets. And so how do you do that? Well, so we want to count number of elements in the union. Well, assume you know the number of elements in this set. And take the number of this set, so the cardinality of this set. And we add the number of elements in A2. Now, is this correct? Well, not really, right? I mean, in many cases, if there are elements here in the intersection, we counted these elements twice. So this is overcounting. So we make up for this by subtracting the number of these elements. And then this is correct. Okay, and so, well, I guess you might say this is kind of obvious, but now let's do this for more sets. Not only for 2 of them, but maybe for 3 of them. Okay, so let's do this here. So let's call this A1, A2, and A3. And we're interested in the number of elements in these sets. So in the total, in the union of these sets. So A1, A2, union A3. And again, we start out by saying, okay, well, maybe we know the elements in the set A1, so we take cardinality of A1, then the cardinality of A2, and then we add cardinality of A3. Now what's happening here? Okay, so let's see what we counted so far. So far we counted all of the elements in here once, all the elements in here, here, and here. Now we go to A2. A2 means that we count this elements in here once, elements in here once, once, once. And now A3 means we count these elements once, these elements once, here, and here. Now what's happening is a lot of overcounting. So we don't get the right answer because we're counting these things twice, here twice, and even the ones in the middle we count them 3 times. So we subtract. And we do that in a symmetric way by subtracting these intersections. Okay, so now what is happening here is, well, we have A1 intersected with A2. So these are the elements in here. So by subtracting them, we're essentially removing one of these little counts. Here, then A1 intersected with A3. So removing this. And finally, A2 intersected with A3. So removing this and removing this guy. So what we see now is that this formula on the right counts all the elements in here just once, but these elements in here, in the intersection of all 3 sets, they don't get counted at all. So they add them in. And now, finally, we get the right answer. Now the right side equals the left side. Okay, so we've just seen how to count the union of 2 sets, then of 3 sets. And let's now, so here's now the general formula. So if you have t sets, so a1 up to at, what you do is, well, you sum cardinality of a1 up to at, then you subtract the sums of all the pairwise intersections, then you add up the triple intersections, or their sums, and so forth, until you finally end up with the intersection of all of the sets. And so maybe for notation, so this is what sometimes called S1, this is S2, and here is ST. So you can just remember it as S1 minus S2 plus S3 minus S4 and so forth. So in the book, this is done a little bit differently. Well, not really differently, but there's a certain notation there. And I wrote it all down here. So let's go slowly through this. So the book talks about the set S. This is the set where these subsets live in. So you should think about it as a big set S where all the elements lie in. Now this set has big N cardinality, so there are so many elements. And now we're talking about having certain conditions, C1 up to CT. So for instance, condition C1 could be, so an example would be that big S is the set of all the pupils going to school, and of these kids, maybe some of them are in class 1, and maybe there are just like 8 classes. Okay, kind of unrealistic, but anyway, you have like 8 classes, and so C1 would be the condition that kid X is in this class. And so you can, so these are conditions, but it can be really anything. So big N of Ci is the number of elements in S satisfying the ith condition. So in other words, this is the number of kids going into the ith class. And so in our picture here, and I like this picture a little bit more, but it's sometimes very convenient to work in this notation, but this picture is a little more like, illustrative. So here we have A1, and that's like, N of C1 is just the cardinality of A1. That's the way you should think about this. And so more notation, Ci, Cj, N of Ci, Cj means the number of elements in S satisfying both conditions, condition Ci and condition Cj. So it's just the intersection, counting the number of elements in the intersection of A, I, and Aj. And if you sometimes divide the bar on top of a condition, it means that this condition does not hold. So N of Ci, Cj, Ck bar means these are all the elements satisfying condition Ci, condition Cj, but do not satisfy Ck. Okay, and now here's the main theorem. So this is the inclusion-exclusion principle in the version of the book. This is theorem 8.1. It tells us something about the number of elements in S that do not satisfy any of these conditions. And here's the formula. It's big N minus, well, N of C1 plus and so forth. And so you see it's very similar to the previous formula you've seen up there. And so this is called S1, S2, up to ST, just as before. And big N, to make this really look nice, is sometimes called S0. And so what do we really count here? Look at this picture here. What do we really count? Well, we count the elements which do not satisfy these conditions. So they are not in, do not lie in A1, do not lie in A2, do not lie in A3. So it's everything outside. So this really counts. So this is really big N minus. It's really the same as the number of elements in S minus the number of elements in the union. And now we see how these two are related, because if we have this formula, now in order to get this formula here, we just take N minus this. So we take N minus S1 plus S2 and so forth. So the formula for the complement is S0 minus S1 plus S2 minus S3 and so forth. Okay, so please do have a look at the examples in the book, 8.1 up to 8.3. So this is very important. Just go slowly through them. So there are some generalizations to the basic inclusion-exclusion principle we've just seen. So here it is again. The number of elements in S satisfying none of the conditions C1 up to Ct, written in this formula, n of C1 bar up to Ct bar, and you find it in theorem 8.1. The formula is you find in the theorem, and you can ask, well, are there different formulas for different questions here? So, for instance, you can think about this here as being that this counts the number of elements in S satisfying precisely 0 of the conditions C1 up to Ct. And then you might say, well, what about if they satisfy precisely 1 of the conditions? So they satisfy precisely 2 of the conditions. And in general, if they satisfy precisely m of the conditions, then this is, you find a formula for this in theorem 8.2. And the book uses this symbol for this number. And you can also think about what about at least 1 of the conditions. Well, think about it. That's something already seen. That means that it lies in the union of these sets, or it's all the elements in S minus those which do not satisfy any of the conditions. And so that's something you've also seen before. But more generally, you can think about what if they satisfy at least m conditions. The symbol here is Lm, and you find that result in corollary 8.2. So here you see the inclusion-exclusion principle again. And there are 2 important applications. So there are many, but here are 2 important applications I would like to talk about now. So first is a proof of that crazy formula we had for the number of surjective functions. And so at that time we had really was kind of not really completely clear where this came from, and it looked complicated. And so here now we can finally prove this. So we call the setting. So we are talking about surjective functions from a set A to a set B. And so A has R elements and B has N elements. And so how do we set this up in terms of inclusion-exclusion principle? Well, first, we need our big set S. Well, this is clearly the set of all the functions. From A to B. Next, we need the conditions. So this is the point where you have to think about what you really want. Well, we want to count something. And here's the, if you want to use this formula, you should make sure that what you want to count can be expressed in this form. Meaning, these are the number of, you want to express the surjective functions as the functions satisfying, well, that do not satisfy condition C1 up to Ct. So what could these conditions be? What could T be? Well, if you think a little bit about it, the important thing about a surjective function is that every element in B is in the range. So we could just make sure that, so T could be the number of elements in B, so T is N. And so Ci goes from 1 up to N, so I from 1 to N. We define Ci as a condition that a function f, the element I in B, well, now, should it be in the range or should it be not in the range? We want that the surjective functions are the ones that do not satisfy these conditions. So that means we want that the ith element is not in the range. And so it reads now as follows. Ci is a condition for the function f that the ith element in B is not in the range of f. Okay, so you should treat this as the ith element in B. And now, well, this looks good. number of surjective functions, a to b, is now equal to this number here, where the t is now n. Okay? So let's compute this. So this is really the most difficult part, in many cases, to come up with the right CIs. Now, in this case, we can now really just plug in the formula, and then we have to find out, and again, think about how we have to evaluate all of these expressions. So let's do this. Okay, n. Big N is the number of elements in S. This are the number of functions from A to B. Well, we know that. This is n to the r. Minus. Okay, so now we have this bracket. And we have to know what is n of C1. Okay, n of C1 are the functions going from A to B, where the first element here, so we have n elements in B, the first element is not in the range. What does that mean for the function f? It means that essentially you can think about it that all the elements in here, they won't map to 1, they will map to the other elements. So it's essentially we're just counting all functions going from A to a set with n minus 1 elements. There are n minus 1 to the r of these functions. And now the same for n of C2. Same argument gives us again n minus 1 to the r, and so forth. Now, how often do we count this? Well, we have n of C1 plus n of C2 up to n of Cn. So we count this n times. So we can write this, and maybe let's do this here. N times n minus 1 to the r. Well, we haven't finished our calculation. Now plus, what about n of C1, C2? These are all the functions going from A to B, such that 1 is not in the range and 2 is not in the range. So essentially, this means the range is somehow contained in this set. So as we are just counting all the functions going from a set with r elements to a set with n minus 2 elements, well, there are n minus 2 to the r of these. And that argument really didn't depend on whether it was C1, C2, or whether it was C1, C3, and so forth. So we always get the same. We always get the same number here. Now, how often did we do that? Well, how many summands are here in this sum, in this bracket? These are precisely the number of subsets of order 2 in a set with n elements. So this is n over 2. We have n over 2 summands here. And so this is plus n over 2 times n minus 2 to the r. And now we see how this works. You can work it out for all of these summands here. And then we get this alternating formula, which will look very similar to you because this is what you already have seen. Okay, so here's the second application. Derangements. So what's a derangement? A derangement is a permutation, let's say, of n elements that leaves no element fixed. So think about like you have 3 books, or maybe you just exchange book number 2 and 3 when book number 1 stays its place, but maybe you want to shift 1 to 2, 2 to 3, and the third book to the first position. In that case, this would be a derangement. And so the goal, of course, is to count these. How many derangements are there? Many, not so many. Well, if you, again, we want to use inclusion, exclusion. So we want to write dn, the number of these derangements as n of C1 bar up to Ct bar. How do we do that? Well, what is the overall set? The overall set is the set of permutations from 1 up to, of these n elements. Now, what could be C1 or Ct? What could these conditions be? Remember again, we want that, so we want to have the bar on this. So we want to think about the definition. It says that no element stays fixed. Okay, so it would be good, again, in this case, to have precisely n conditions. And so Ci should be the condition that the ith element stays fixed or does not stay fixed. Well, we want this that no element stays fixed, which means that in this case, all of these elements should stay fixed. So this is a condition that the ith element that I stays fixed. And so these are, again, I goes from 1 up to n. So we have n conditions. Okay, that looks good. So this is set up. Now we have to go from here to here. And this is something where I really want you to think about it a little bit. So do it yourself. Think about it in the same way we solved the previous problem. And for instance, think about what it means if you have a permutation where the first element stays fixed. Essentially, this is just a permutation of the other n-1 elements. Think about it and you will come up with this. Or read about it in the book. So I claim that using this inclusion-exclusion principle, we can find this expression. Now let's simplify it. This is n times n-1 factorial. So this is just n factorial. Now n over 2 times n-2 factorial. If you write it down, if you express this as n factorial divided by 2 factorial times n-2 factorial. So n factorial divided by 2 factorial divided by n-2 factorial times n-2 factorial. Everything cancels out. You only get this. You can do that for the other summands too. Now we multiply out n factorial. So you get n factorial times, big bracket, 1 minus 1 plus 1 divided by 2 factorial minus 1 divided by 3 factorial. Plus or minus, always alternatingly, and so forth. So you can write in this form. N factorial times sum over k from k to x 0 to n, 1 over k factorial times minus 1 to the k. This is the same thing. Now why is this great? Well, because maybe, I hope lots of you, if I see something like this, immediately know what I'm talking about. If you would replace this by x, then you should know that this is just the first part of the infinite series which gives you the exponential function. Right? It only goes up to n. It doesn't go up to infinity. It would be infinity here. Then you would have, actually, if it would be infinity here, you would have n factorial times, well, e to the x, no, e to the minus 1. But because we only go up to the nth term, this is just roughly the same. So this is roughly n factorial times e to the minus 1. And so I want you to think about that. This is very nice by solving the following homework. So estimate the probability that if you shuffle 1,000 books, like randomly, look at all the possibilities, that no book stays at the same place. So among all of these, lots and lots of permutations, how many of these are derangements? And how many are not? And so what's the probability that if you do that, you shuffle just some of them, no book stays in the same place, and you will notice that you don't have a good intuition from this. I would be surprised if you would know what would be the answer. Okay, so see you next week.